Hello, welcome to the NPTEL online certification course on deep learning. So, in our previous lecture, we have started discussion on some of the popular convolutional neural network architectures. So, we have talked about LeNet 5 and we said that the LeNet 5 was a network which was used in earlier days by different banks for automation of recognition of the numerical values written in the bank checks. And then we had introduced one challenge, which is ImageNet large scale visual recognition challenge, and we said that day that the subsequent networks or the network models that we will discuss are basically the champions or very successful submissions to one of these visual recognition challenges. And this visual recognition challenge that actually encourages the researchers to compare and to monitor what is the progress of computer vision research across the globe. And we have said that the ImageNet database that contains more than or few million image databases, and today we are going to discuss about a popular convolutional neural network model which is AlexNet, and AlexNet was the winner of 2012 ImageNet large scale visual recognition challenge. So before we go to the architecture of AlexNet, let us see that what kind of images does this ImageNet contain, or what is the nature of the database. So here what I have shown is just few samples from the ImageNet database, and you find that there are images from dogs, there are images from birds, there are images from horses, images from cars and all that. So we said earlier that this ImageNet database contains 1000 such categories of images, and in every category there are thousands of images. So in total, the total number of images this ImageNet database contains is around 15 million. So some of those images are used for the training purpose, some of those images are used for testing and validation purpose. So this ImageNet database is a huge database which is available to the computer vision researchers, and they can use this ImageNet database for designing, training and validation of the deep neural networks that the researchers design. So now let us come to what is this AlexNet. So as shown here, the functional diagram of AlexNet network or convolutional network, you find that the AlexNet contains a number of convolution layers. It contains a number of pooling layers. So pooling, which is used in AlexNet, is actually max pool operations. It also contains a number of fully connected nets, and the output layer, which is a 1000 channel softmax layer. So why this 1000 channel softmax layer? We have said that the AlexNet database or the ImageNet database, it contains 1000 different categories of images. So at the final output, we have one node for each of these 1000 categories. So as there are 1000 different categories of images, so we have 1000 different nodes in the output layer, and this output layer is actually a softmax layer. So you find that the input to the AlexNet is an RGB image. So it is having three different channels: the red channel, green channel and blue channel. Then the first convolution layer in the AlexNet, that has convolution kernels of size 11 by 11. So here you can find that you have convolution kernels where the kernel size is 11 by 11, and width tide is equal to 4, and it has 96 different kernels. So as a result, from the output, the first convolutional layer output, gives you 96 different channels, because there are 96 different kernels. So the output contains 96 different feature maps, and each of the feature map contains features of size 55 by 55, and that comes from this calculation, as every input is of size 227 by 227, and you have convolution kernels of size 11 by 11. So as we said before in our previous class, that I can compute what will be the feature size. So the feature size will be simply 227 minus 11 divided by 4, because 4 is the stride, plus 1, which gives you 55. So every feature map after the first convolution layer is of size 55 by 55. Then after this convolution layer, you have the overlapping max pool layer, where the max pooling is done over an window of 3 by 3 and stride is equal to 2. So here you find that because our max pooling window is of size 3 by 3 but stride is 2, that means the max pooling will be done over overlapped windows. And after max pooling, you reduce the size of every feature map to size 27 by 27, and the number of feature channels, that remains 96. Then you have the second convolution layer, where the convolution kernel size is 5 by 5, and in this case you use a padding so that the output of the convolution layer remains same as the input feature size. So the size of the feature maps generated by the second convolution layer remains same as the input feature map size. And the number of kernels in this case is 256. So that means from this convolution layer output, you get 256 different channels or different feature maps. And every feature map is of size 27 by 27. Then again you have an overlapping max pool layer, where max pooling is again done over an window of size 3 by 3 and stride is equal to 2. So again that means that max pooling is done over overlapping windows. And output of this becomes your 13 by 13 feature maps, and the number of channels you have 256, because to max pooling you are not reducing the number of channels. After this, you have 3 consecutive convolution layers. So the first convolution layer is having kernel size of 3 by 3 with padding equal to 1, and there are 384 kernels. So that gives you 13 by 13 feature maps, and there are 384 feature maps, which passes to the next convolution layer. Again the convolution kernel size is 13 by 13 with padding equal to 1, and this has 384 number of kernels. That means output of this convolution layer will have again 384 number of channels on 384 number of feature maps, and every feature map is of size 13 by 13. It is because you find that you have given a padding equal to 1 for a 3 by 3 kernel size, and that is the reason that your feature map size, the size of every feature map at the output of this convolution layer, is remaining same as the size of the feature maps which are inputted to this convolution layer. This again passes to another convolution layer, where the convolution kernel size is again 3 by 3, padding equal to 1. That means output of this convolution layer will generate the feature maps, where the feature map size will remain the same, that is 13 by 13. But in this case, over here, what AlexNet uses is 256 kernels. So that means at the input of this convolution layer, there are 384 channels, and these 384 channels now gets converted to 256 channels, or it generates 256 feature maps, and every feature map is of size 13 by 13. Followed by this is the next overlapping max pool layer. Again the max pooling is done over window of 3 by 3 with stride equal to 2, and that gives you the output feature map, and the number of channels remains the same, which is 256, and the size of every feature map is 6 by 6. After this, what you have is fully connected layers, or which are same as your multi-layer perceptrons that we have discussed earlier. So the first two fully connected layers have 4096 nodes each. So you find that after output of this max pool layer, we have 6 into 6 into 256, that is 9216 number of nodes or number of features. Okay, and each of them is connected to each of the nodes in this first fully connected layer. So the number of connections or the number of parameters that we will have in this case is 9216 into 4096. And then from this first fully connected convolution layer, every node of this first fully connected layer provides input to every node in the second fully connected layer. So here you have number of connections which are 4096 by 4096, because the number of nodes in the second fully connected layer is also 4096. And then we have the final layer, which is the output layer having 1000 softmax channels. So this is a softmax layer, and the number of connections from this fully connected layer to this output layer, that is again 4096 into 1000. So this is overall the architecture of the AlexNet, or the functional diagram of the AlexNet. And if you look at the architecture looks something like this. So you find that the entire AlexNet is actually implemented in two channels. Okay, half of the network is put in one channel and half of the network is put in the second channel. And because they are in two different channels, so that made it possible to train this network on two GPU cards. So coming to some specific features of this AlexNet, you will find that this AlexNet contains more than 60 million parameters, and it has around 6,50,000 neurons. And as we have just shown, the network is split into two pipelines, which makes it possible to train the network on two GPUs. Of course, even then, it took almost 1 week to train this network fully. The input image size actually is 256 by 256 in 3 channels, that is red, green and blue channels. And because AlexNet takes the color input in 3 different channels, red, green and blue, so even if we input a gray label image, which is having just one channel, so the gray label images are to be replicated into 3 channels R, G and B, so that they can be accepted by AlexNet. And to fit the input, as we have seen that the first over here, the input to the AlexNet is 127 by 127 pixels. Every channel is 127 by 127 pixels. So when you feed the input for training purpose, though our actual input is 256 by 256 RGB image, but each such images, RGB images, were randomly cropped into size of 127 by 127, and they are fed to the input layer of the AlexNet. For training of the AlexNet, the algorithm which is used, and that is the algorithm which is used by all the neural networks or all the deep neural networks, which is backpropagation learning, as we have said earlier. And this backpropagation learning actually implements stochastic gradient descent operation. And to make this gradient descent algorithm to be more efficient, there is an optimizer which is called momentum optimizer. So this AlexNet, training of the AlexNet, uses this momentum optimizer techniques. So it is stochastic gradient with momentum optimizer. And as you know that the stochastic gradient or the backpropagation learning itself is an optimization technique. So what does it try to optimize? It optimizes the loss at the output of the network that we have seen earlier, right? And by optimization or minimization of the loss, you train the network for your given applications. And this momentum optimizer is another optimization technique. There are other optimization techniques also. We'll see that after a few lectures. So all these optimization techniques basically optimize this backpropagation or gradient descent algorithm itself with the aim that your gradient descent algorithm becomes more efficient. And once the network was fully trained, the network gave a top 5 error rate of around 15.3%. So what is meant by this top 5 error rate? You find that you remember through our earlier discussion that as the AlexNet contains 1000 output nodes, every output corresponding to one of the image categories. So when you test with a given input for which the category is unknown, what the network will do? At every output node of the network, that is the softmax layer, you get a score of the input that you have provided to the corresponding category. That means every output or the score output that you get from the output softmax layer, every output node gives you a score function to the corresponding category. Now, if you arrange these scores into, say, descending order of magnitude, then the first output becomes the score for the most preferred category. The second output score gives you the score for the second preferred category, and so on. So the top 5 error rate says that if I take the top 5 such categories to which the network has classified the input that you have provided, your actual class should be in one of those top 5. If it is not in any of those top 5 categories, that indicates an error. So that is what is your top 5 error, and in this case, this AlexNet gives you a top 5 error rate of 15.3%. So in all our subsequent discussions, we will talk about top n error rate. So that should be clear what is meant by your top n error rate or top 5 error rate. So these are the features of the AlexNet. Then earlier we also discussed about a problem called vanishing gradient problem, and we have seen that if your nonlinear activation function is a sigmoidal function or a tan hyperbolic function, then it gives a risk of vanishing gradient. That means in some cases, as you are training the network with the gradient descent procedure, vanishing gradient means that the gradient of the error function may become too small, so that using that gradient, when you try to update the network parameters, the update becomes almost negligible because the gradient itself is very small. That is what is your vanishing gradient problem. And why do you get this vanishing gradient problem? It is because if you remember, that our sigmoidal function was something like this, right? So it gets saturated at 1 where your input parameter x becomes very high. Similarly, it saturates to 0 when the input parameter is very low on the negative side, right? Because over here your output saturates to 0, saturates to 1, and over here output saturates to 0. So if your argument is somewhere over here, you try to take the gradient of the output with respect to argument, this gradient is almost 0. So the same is true if your nonlinear activation is sigmoidal function or the nonlinear activation is tan hyperbolic function. Whereas in case of ReLU, you remember from our earlier discussions that ReLU activation function is something like this, which is rectified linear unit. So on this side, your gradient never vanishes. The gradient is almost constant. So that is the advantage that you get using ReLU as a nonlinear activation function. But it has other problem, that unlike in case of the sigmoidal activation or tan hyperbolic activation, where the activation output is limited, is bounded, in case of ReLU, the output is unbounded. As x increases, the nonlinear output, the activation function also keeps on increasing. So that's the problem with the ReLU when ReLU is used as a nonlinear activation function. So to avoid this problem, what AlexNet does is it tries to normalize the output through a process which is known as local response normalization. So this LRN, or local response normalization, it carries out a normalization operation by amplifying the excited neurons while dampening the surrounding neurons at the same time in a local neighborhood. And this particular operation is encouraged from a phenomenon known as lateral inhibition concept in neurobiology, which actually indicates the capacity of a neuron to reduce the activity of its neighbors. So this AlexNet, in order to deal with the problem of unbounded output, it goes for a normalization of the output before applying this nonlinear activation function. So that is how it avoids the unbounded problem, and at the same time it avoids the vanishing gradient problem. So this local response normalization, it can be done across the channels. Also, it can be done within a channel. So when you do this local response normalization across the channel, this is what is known as inter-channel normalization. And in case of inter-channel normalization, the operation is done in this way. Suppose IXY is the response at location XY in your feature map, and the index I indicates the ith channel. So BIXI is the output at location XY in the ith channel, and AIXY is the original value at location XY in the ith channel. So the way the normalization is done is by this. You normalize this AIXY by a factor which is given by k plus alpha times sum of AJXY, where this j varies within neighboring channels. So j varies from maximum of 0 to I minus n by 2 to minimum of n minus 1 and I plus n by 2. That means you take n by 2 number of channels before and n by 2 number of channels after. This max and min operations with 0 and n minus 1 as arguments is put to take care of the first channel, featured channel, and the last featured channel if there are total n number of featured channels. So this is what is your local response normalization, where the normalization is carried over subsequent channels. So the nature of output that you get using this local response normalization is something like this. So here, these are the feature values of different channels before normalization, and these are the feature values that you get after the normalization across the channels is carried out. So here you find that when you use this normalization, your output actually becomes bounded. In fact, every output you find that after normalization becomes less than 1. So this is one type of normalization, local response normalization, which is inter-channel LRN, which can be used. And the other kind of normalization that can be used is what is intra-channel normalization, where the intra-channel normalization is carried over the features within the same channel. So here again, if I want to apply this inter-channel normalization in channel I, again you find that BIXY is the feature value after normalization at location XY in the ith channel, and AIXY is the feature value at the same location XY in the ith channel before normalization. So here what you do is you normalize this feature value by again a factor k plus alpha times take the summation of square of the feature values within neighborhood of xy. And again, here the neighborhood size is say n by n, and again max and mean operations are performed to take care of the boundary features or features which are at the boundary of the feature frames. Okay. Why k is used is to avoid division by 0. In case this particular summation term within this factor, this becomes 0, k is a very small positive value. So k takes care of the fact that I don't encounter any situation of division by 0. And you find that this k and alpha, they are actually hyperparameters, so which has to be chosen by the designer. So this is another kind of normalization, which is inter-channel normalization that can be performed for this local response normalization operation. And here again, you find that after normalization, the kind of output that you get. So here on the left hand side, you have the feature values before normalization, and on the right hand side, we have the feature values after normalization. And here again, you find that after normalization, the feature values have been bounded. Okay. So this is how, using the local response normalization techniques, the AlexNet could take care of the unbounded output problem of rectified linear unit, which is the nonlinear activation function, which is used in AlexNet. Other problem in AlexNet you find is that, as we said, that the number of parameters in AlexNet is more than 60 million. Obviously, with such a huge number of parameters, there is always a risk that while you train this network, there will be a problem of overfitting. So what is this problem of overfitting? Overfitting means that the network will try to learn, or it will perform very well on your training data set, or it will try to memorize the training data set, but in the process, it will not be able to code the general properties or the features of the input data. So as a result, your training performance may be very high, whereas the performance during training or the generalization error may not be acceptable. So to avoid this overfitting problem, or to reduce this overfitting problem, during training, additional data or augmented data, training data was generated from the existing data. And this augmentation was done by data mirroring, and the augmentation was also done by taking random crops from the input data. So you have different multiples of the input data, right, by which the network was trained, so that the network can code the features or the descriptors, the general descriptors of the input data. The other way this overfitting problem was reduced is by taking a regularization approach, where the regularization was a dropout regularization. So let us see what is this dropout regularization. This dropout regularization is a technique which was proposed by Srivastav et al. In the year 2014. So what is done in this dropout regularization is that during training, randomly selected neurons or randomly selected nodes, which are selected with a probability of say 0.5, were dropped from the network. So the probability that a node will exist in the network is 0.5. Similarly, the probability that it will be dropped out is also 0.5. So what does this dropout means? That a node which is dropped out, that node will not pass its output to the subsequent nodes, or to the nodes in the subsequent layers downstream. And at the same time, during backward pass, for those nodes, no updates of the input weights will also be taken place. So that means, as if you are simply removing that particular node and the associated connections from the network during the training process. So how do you gain by this dropout? So here you said that while training, the weights of the neuron are tuned to some specific features that gives some sort of specialization to the neurons. And the neighboring neurons also starts relying on these specializations, which is known as co-adaptation. And that leads to a problem that neural network becomes too specialized to the training data. And through dropout, what you are doing is, as you are removing some of the neurons at random, that means we have to have other neurons to take over the charges of these dropped out neurons. So as a result, the neural network learns multiple independent representations. And that is how it avoids the problem of overfitting, and your neural network becomes more general. So this previous diagram shows that some of the neurons which are dropped out during the training process, so the neurons which are white, they are dropped out during the training process. So in different training epochs, the neurons will be dropped out at random. So it is not that the same neuron will be dropped out every time. So that is what is your probability, that is decided by the dropout probability. So as a result, what you gain is something like this. The network becomes less sensitive to the specific weights, and it enhances the generalization capability of the network, and as a result, it becomes less vulnerable to the overfitting problem. Okay. So this is what is done only during the training process, but during the testing, the entire network is used. That is no dropout at the time of testing. Obviously, while training, as we are dropping out some of the neurons, so the number of iterations which will be required to train the network will be more. That means your training time increases. But at the same time, on the positive side, what you have is that it helps overfitting problem, so that your network becomes more general and it captures the salient features of the input data. It does not simply memorize the input data, and that gives better performance. The network gives better performance with such a type of training. So we'll stop here today. In the next class, we'll try to go through some other popular CNN architectures, and we'll also discuss about some challenges that you face while training of the deep neural networks. Thank you.